So a subgroup H of a larger group G, sometimes we'll call that the parent group. H is a subgroup of G. If H is a group in its own right, so it has to have associativity, it has to have an identity element, it has to have inverses for every element, and it has to be closed under the operation. But the question is, what operation? If we could choose whatever operation we wanted to for H, we could say that H is, in fact, a group, right? This set, together with the operation of multiplication of real numbers, is a group. We can all agree on that, I think. Multiplication of real numbers is associative. There is an identity element in this group, namely, what's the identity element? 1. It's the multiplicative identity. Why is it closed under multiplication? 1 times 1 is 1. It's the only thing we can do in this group. And what's the inverse of 1? 1, for that very same reason. So this does meet the criteria to be a group, but it does not meet the criteria to be a subgroup of G, because the operation in my smaller setting has to agree with the operation in my larger setting. It has to inherit that operation from its parent group. So it's not a subgroup.
So do we have a term for a subset of a group that acts as a group under a different operation of its parent group?
We do not. Not that I'm aware of. There's no terminology for this situation. If we're changing the operation, we are completely changing the algebra. Right? And so I would argue that the only similarity that this bears to this has nothing to do with groups and only has to do with sets. Right? The set of elements of this group turns out to be a subset of the set of elements of this group. But beyond that, we can't really say that there's any other algebraic relationship between those two things. So that's an important point. It's the only reason why there's sort of one extra thing to think about when you're thinking about subgroups instead of groups themselves, is that operation in the subgroup has to have been the operation inherited from the parent group. So at the end of class, I invited you with your small groups to start drafting up a proof for these two parts of question number 5. And question number 5 asks that if I have a group G and an element in that group A, and I define a subset of elements of G in this way. So it's the set of all integer powers of A, which next chapter we're going to start calling that the cyclic subgroup generated by A. So if I define this subset of elements, what I'd like to know ultimately is that subset in fact a subgroup of G? And I'm not asking you to prove that whole thing here, but I am asking you to do one piece of it, namely to prove that H has the closure property, which means that if I take any two elements of H, G and H, and I operate them together, GH, that product is also an element of H. And I'm using the word product here when what I really mean is that the application of the operation of my group to G and H. Right? So one of the early bits of confusion that I want to make sure we all have clear is that when I write an exponent, so a to the power k, what I really mean is not necessarily multiplying a by itself repeatedly, but using the group operation on a with itself repeatedly. So whatever that operation happens to mean, we do that operation on k copies of a. And because of associativity, we can do whichever of them first and whichever of them afterwards that we wanted to. So we string together a bunch of operations on a, is what we mean by a to the power k. And so I think the trickiest part about these kinds of proofs is just getting the structure laid out. So if I get out my cocktail napkin over here, what I would want to do if I were trying to draft up a proof of this and just sort of exploring, I would want to know how to translate each of these statements into something algebraic and actionable, something that gives me an equation I can do something with, right? How do I know that when I multiply two elements of H that I get an element of H? Well, if I'm proving this directly, I'll be able to assume these two things and then try to deduce this one. And assuming that G belongs to H means something. Right? It means, going back to the definition of H, that G belongs to the set of all integer powers of A, this element A. So G is equal to A to some power. And I don't know what we want to call our power. Let's call it P or something like that. And then somewhere in my napkin, or at least in my mind, I will remember that this P is some integer, because those are that's the quantifying set for the K's that define my thing. And then likewise, if H belongs to capital H, then that means that it, too, is some integer power of this element A, some Q, which is an element of Z. And then finally, in order to show that GH is an element of H, I need to show that GH is also some integer power. Let's say A to the power R for some R. And so then, now that I've done this reframing, now I know kind of what my roadmap is going to look like. I need to show that when I multiply this by this, that I get something that looks like this. And the more that I can be explicit about why it is that GH is equal to A to some power R, then the better my proof will be for the reader. So getting this all sort of sketched out on your napkin and then figuring out how to turn this assumption into that deduction is really the name of the game. So talk about these two proofs in your small groups on Slack between now and Friday's class, and we'll reconvene in our small groups to see what you've come up with at the beginning of Friday.